So we will wait for 1 more minute. So let us begin this session. So welcome to the third day sessions. So today we are going to witness the lectures from Professor Mainak Thakur, faculty member of IIIT City. He is going to give us talks on basic analysis techniques as well as hypothesis testing. To introduce Professor Mainak Thakur, he did his PhD from IIT Kharagpur, also his MS from IIT Kharagpur. He has several achievements to his credit. He was invited speaker to present his research work at international conference on air quality forecasting using big data and machine learning algorithms at Anyang University Graduate School. And he presented a poster and a paper in the most prestigious conference in India and abroad. He attended a summer school and workshop on data science and engineering in Brest, France. He is ranked 29 in JAM examination. He is ranked 148 in GATE 2010. He is ranked 89 in JECA examination. And also he is a member of bronze winning LLR interball football team. So he is a football player, obviously. And the most surprising thing is that he got the best director award in a short film festival for directing a short film. So along with this one, he has several journal papers, conference papers. He is guiding several PhD students here at IIIT CCT. So now with this introduction, now the dais is given to Professor Mainak.
Thank you, sir, for such nice introduction. Am I audible? Is it? Yes. So actually, my voice is recovering. I was down with fever since last 3 days, so maybe I'll not be able to speak very loud. Okay. So I'm sharing my screen. Let me know if it is visible. Okay. So is this visible?
Okay.
Yes.
Yes.
Visible.
Okay. So the first part of our lecture, as was mentioned, is basic analysis techniques and introduction. There are three parts here. One is probability distributions, then sampling distributions, then central limit theorem. This is very useful topics, well chosen, and I think 50 minutes is a little less for this because there are many distributions, so we can only talk about a few within limited time. There are many things about central limit theorems, sampling distributions, and all. We'll talk about the relevant things, which will help us to move forward. If there is any question or anything, you can stop me anytime and ask questions. Okay, we'll try to finish it within time. Let's see. In order to do so, maybe I will assume some. I don't have any idea about the audience proficiency about probability. So I'll assume that basic probability course everyone has done. So with that assumption, I'm going forward, so I can skip a very basic thing. A few basic things I maybe skipped in order to maintain the time. Okay. So when we talk about probability distributions of what? Of random variables. So we need to start with random variables. What are random variables? So very specifically, there is the name is very confusing. Random variable is not random, it's not variable at all. Okay, so it's not at all a random thing, it's not at all a variable thing, it's only a function. So mathematically speaking, random variable is a real valued function defined over a sample space. Now sample space is what? Sample space is set of all outcomes coming from a random experiment. Their random experiment is there, so from their random part is taken. But if you talk about random variable, it's only a function. You give an outcome, we can give you a value, okay, real value. That is random variable, that function is the random variable. So what is sample space? Sample space means, let's say you are tossing a coin. What will be the sample space? Head and tail, these are the outcomes, right? So if I can call head as 0 and tail as 1, so this is a function now, okay, from the set of outcomes or sample space to real valued, right? To real numbers, right? So a function from sample space to real numbers is random variable. It associates a numerical value with each possible outcome of a random experiment. Like I said, that head is an outcome of an experiment. You can associate 1 with head or 0 with head. Okay. Similarly, tail is an outcome. So you can associate 1 or 0 with tail. Okay. Random variable is denoted by capital letters. This is very important. Capital X, capital Y, capital Z, etc. The possible outcomes are denoted by small letters such as small x, small y, z, a, b, c, etc. So outcomes means, let's say 1, 2, these numbers. Okay. These numbers are denoted by small letters. But the random variable x, capital X, random variable y, capital Y, these is only for denoting random variables. Let's talk about one example. 2 coins are tossed. What are the possible outcomes? These will be the possible outcomes: head head, head tail, tail head, tail tail. Now you can associate, for with each outcome you can associate one probability, right? H, this probability of happening this event is 1/4. This is 1/4. This is 1/4. This is 1/4, right? So you can associate probability. Now maybe in most of the practical situations, we don't need probability of each of the events separately. We don't need to know each of the events. Rather, we may be interested in some time let's say in the cases, so probability, let's say we may be interested in finding probability of happening of 2 heads. Okay, 2 heads means only this case. One head means these two outcomes are mapped to one, right? This is now a random variable. Zero head in this case. So the random variable associated with this event is zero. Now we can consider a random variable x, which is number of heads obtained in a trial. Okay, trial means one trial you are doing. This one trial means two coins are tossed together. This is the outcome, or this is the outcome, or this is the outcome, or this may be the outcome. Now x, if it is a number of heads obtained in a trial, x may take three values, 0, 1, or 2. Okay, as we saw, there may not, I mean, there is no other value x can take. So for a fair coin, probability of x equals to 0 is only this case, which is 1 by 4. On this case, x equals to 1, x equals to 1, these both of them are 1 by 4. So x equals to 1 corresponds to these two cases. So it is 1 by 4 plus 1 by 4, half. Probability of x equals to 1 is half. Probability of x equals to 2, two heads, is 1/4. We all know this. So if you draw the probability distribution, this is the probability distribution, how probability is distributed over the different values of random variables. There are the three different values, 0, 1, 2. All other values over this x line, probability is 0. Correct. So this may be a very raw version of probability distribution, and if you plot it, it will look like this: half, this is half, this is 1/4, this is 1/4. X equals to 0 is 1/4, x equals to 2 is 1/4. Okay, I hope this is clear. There is something called cumulative distribution function. Okay, this is not cumulative distribution function, this is normal probability mass function. Actually, we'll talk about it later, the definition and all. Cumulative distribution function is defined as probability of the random variable x taking less than equals to small x. Okay, so now this is a function of small x, if small x, right? So for different values of small x, let's say if x1, x is small x is 1, this will be probability of x capital X less than equals to 1, right? So what will be the, so the, if we define cumulative distribution function in this manner, you know, what will be f of minus infinity? Can anyone guess what will be f of minus infinity? It will be probability of x capital X less than equals to minus infinity.
0.
This will be 0. Probability of, let's say, f of infinity will be
1.
1. Correct. So these are properties of a cumulative distribution function. So f of minus infinity will be 0. F of infinity is covering all the probabilities. Now, if you think of 1 by 4 plus half plus 1 by 4, this is 1, right? So if you take x here, somewhere here, let's say 2.5, capital X is, let's say 2.5, you take x here. So f of x of 2.5 will be probability of capital X less than equals to 2.5, right? So what will be probability of x less than equals to 2.5? X equals to 2 will come, x equals to 1 will come, x equals to 0 will come. The summation of them is 1, right? So any value greater than 2 or greater than equal to 2 will give you 1 for CDF. This is very simple definition. What will be the CDF of the random variable corresponding to example 1? F of 0 will be 1/4, f of 1 will be 3/4, f of 2 will be 1. Any value greater than 2 is 1. Any value greater than, for any value greater than 2, f of x will be 1. If for any value, f of any value x which is less than 0 will be, f of that value will be 0. F of x less than 0 will be 0. So like that, cumulative distribution function is defined for, it should be defined for all x. That's what it is meant. So only we have only defined for 0, 1, 2, but as x is a real line, so it should be defined for all x. There are two types of random variables. One is discrete random variable, another is continuous random variable. What is discrete random variable? It takes finite or countable number of distinct values. So it takes only distinct values. Let's say the number of children in a family. It can be 0, it can be 1, it can be 2, it can be 3. Some distinct values it is taking. Or sometimes it is infinitely countable, but infinite numbers. That is also possible. Okay. Let's say example is how many, let's say you are tossing a coin and number of heads before getting the first tail is a random variable, but it may take 0, 1, 2, 3, 4 up to infinity. Okay, it's possible that you are not getting any head, you are not getting any tail, so there will be infinite number of heads. So like that, these are discrete random variables. This, what is continuous random variable, similar to discrete, but they take values in continuous intervals. Okay, like x is height of a person, or weight of a child at birth, or waiting time for a bus, etc. Okay, so if consider height of a person, what is the the event, or x may take values between 4 feet to 5 feet, right, or 4 feet to 6 feet, whatever, but any value. Okay, any value between 4 feet to 5 feet x can take. It's not distinct. These are not discrete values. 4 feet 1.26 inches. Okay, possible. PMF is probability mass function. PMF is defined for, now one more thing, cumulative distribution function is there for both discrete case, discrete random variable, and continuous random variable. Okay, it may be defined for both of these types of random variable, but PMF is defined only for discrete random variable. But what is the definition? It's simple. Probability of x equals to xi is pi. Okay, for different xi's are value that x is taking. Okay, x is a discrete random variable, so x will take distinct values like x1, x2, x3 to xn, or goes to the sequence, goes to infinity. So probability of capital X equals to xi is pi for all I. Okay, this is the simple definition of PMF. Okay, so PMF can be we have already seen PMF here. Probability of x equals to xi, let's say xi is 0, it's 1/4. 1/4 is pi. Okay, first one is p1. Let's say x equals to x1 is 0, this is p1. X equals to x2, this is p2. X equals to x3, this is p3. Okay, and we have drawn this PMF also. So it's very simple. Summation pi's will always be 1, and you can convert convert PMF to CDF also, because fxx is probability of x less than equals to x, which is summation of all pi's for which xi is less than equals to x. Okay, you can take up to x, whatever probability is there, you are summing them. Okay, so like that you can get CDF from PMF. Now PMF works only for discrete random variable. PDF is probability density function. It is defined only for continuous random variable. Okay, PDF of continuous random variable x is a non-negative function fx. This is called probability density function fx, such that probability of capital X, this is the random variable lying between two possible values a and b. Okay, two values is equal to integrating a to b, integrating limit from lower limit a to upper limit b, f of t dt. Okay, f of t, fx is the density function. Okay, so if you integrate the density function from a to b, you will get the this probability. Integration is what? Integration is area under the curve, right? So if you have the curve fx from a to b, whatever the area under the curve will come, that is the probability from a to b. X less than equals to a, less x greater than equals to a, less than equals to b, right? So if you integrate from minus infinity to infinity, the total probability will come, that is 1, right? So area under the curve from minus infinity to infinity will be 1 for the density function, and it's a non-negative function, of course. PDF to CDF, how do you find? Fx is probability of x less than capital X less than equals to x, right? So till x, whatever density is there, you are integrating. Integration is nothing but summation, right? So it's in the continuous form, it is integration. So integration from minus infinity to x, ft dt will give you fx, capital Fx, which is CDF. Okay. So there are 2-3 important properties. There are many important properties for distributions. One, two, three of them we are giving. These are related to moments. So expectation of x, which is mean. Okay, expectation of x is summation of xk into pk, right? Pk means the probabilities. The happening of xk is the probability of happening of xk is pk. Okay, so if you are summing all the values with their probabilities, you will get expectation. Okay, this is for discrete random variable. For continuous random variable, instead of summation, you need to integrate from minus infinity to infinity. Xk will become x here, pk is corresponding density. So x into fx dx, you will integrate. This is average only. So it's if you have, let's say, if you have, let's say, 5-6 values, how do you find average or mean? You sum them and divide by n, right? In that case, pk is 1 by n for each of the cases, right? So if we give equal weight, this is simple average. If we give different weights, you will get different average, right? Weighted average. So this is average only. This is mean. How do you find mean? This EMF. How do you find what will be the mean of this case? Mean in this case. Mean of expectation of x for this random variable. Can anyone guess?
It is 1 here.
Yeah, it's 1 because 0 into 1 by 4 plus 1 into half plus 2 into 1 by 4. This gives 1. Okay, you can see here also it's actually symmetric kind of distribution where 1 is more and 0 and 2, both side it is well balanced. So the mean will be 1 only. Okay. Now let's move into the distributions. Okay, we'll quickly cover few probability distributions. That is the first part of our topic. Bernoulli random variable. Okay, Bernoulli random variable is a very useful and widely used, very common and very simple distribution or simple random variable. So what is Bernoulli trial? Let's understand first. A trial that has only two possible outcomes, often called success and failure. Okay, let's say you are tossing a coin. If you consider head as success, tail as failure, this is a Bernoulli trial. Okay, tossing a coin is a Bernoulli trial. Now, X, if it is following Bernoulli distribution, Bernoulli has one Bernoulli random variable or distribution has one parameter P. Okay, parameter is also we need to discuss. Parameter is something that defines the distribution. Okay, so if you change P, the distribution form will change. Okay, but the distribution is actually dependent on P. So if you change the P value, the distribution will change, but the form of the distribution as such is not changing. For different P values, the probabilities, all these things will change. Okay, PMF structure will change. Okay, so here P is the probability of success. Okay, let's call the success as 1 and its probability is as P. Success, failure is 0 and its probability is 1 minus P. Only two cases are there, so if it is P, it will be 1 minus P. Example is simple coin tossing. Probability of head is half, P can be half, P can be less than half also. If it is unfair coin, you can see this PMF. This is PMF of an unfair coin. Okay, where P is less than 1 minus P. That means, let's say P is 1/3, so 1 minus P will be 2/3, right? So that's what this case is. So probability of failure is more than probability of success. That means if it is unfair, probability of head is 1/3, probability of tail is 2/3. So the it's unbiased. It's biased coin. Okay, so it's biased coin. That means probability of head and probability of tail is not same. That means it's possible that if you toss 30 times, you will get 10 heads and 20 tails around, approximately. Okay, how do you find expectation of X? Is very simple. P into 1 plus 0 into 1 minus P. It's P. Okay, mean is P and variance for this distribution is P into 1 minus P. That also you can find. Okay, variance we have not defined. Variance is here. I somehow missed. Variance is expectation of X minus mu whole square. Okay, what is it? The different, what is mu? Mu is this expectation of X. Okay, mu is mean. So the distance between the random variable and its mean, and if you make square, this is another random variable. Okay, so you can consider Y as a random variable, which is X minus mu whole square. Okay, this is another random variable. Expectation of that random variable is variance. Okay, so mean of a random variable, which is the distance between X and its expectation, square. Okay, if you take the expectation of that random variable, it is variance. It gives the the dispersion, how the distribution is dispersed. That means if it is not too dispersed, if it is we'll see in the normal distribution case, your variance will be smaller. If it is dispersed, variance will be larger. Okay, let's see now. The variance of Bernoulli trial also can be found as P into 1 minus P. Binomial distribution is the next one. Binomial is, if you understand Bernoulli well, binomial is easy. So if you are, let's say, conducting n independent Bernoulli trials, okay, n independent Bernoulli trials, that means n trials where only success and failures are there. Okay, let's say n coin toss. Okay, each trial has the same probability of success P. Okay, but you are doing it independently. Now X denotes the number of successes in those n trials. So you are doing n number of heads. Okay, let's say you are doing n number of heads, and how many of them are in number of tosses. Let's say you are doing in number of tosses, how many of them will be heads? This may be a random variable, like that. X is the number of successes in n trials. Okay, so X follows binomial np. It has two parameters now. It is dependent on number of trials and the success probability p. So probability of capital X equals to X is given by this formula. This is the PMF of binomial random variable, NCX, p to the power x into 1 minus p to the power n minus x. And x runs from 0. You know how many successes can be there in experiment, in trials? It may be possible that all failures, that means 0 success. It's possible that 1 success, 2 success, 3 success, or n success. Okay, what is the probability of 0 success? NC0, p to the power 0, 1 minus p to the power n. That will be 1 minus p to the power n. That means, you know, all failures in n number of trials, the first one is 1 minus p, second one is 1 minus p, all 1 minus p. So 1 minus p to the power n. Okay, so like that. Number of heads in n coin toss can be an example. Expectation of X is np. The it's very simple to understand why it is np. Let's say you are doing 10 coin toss. Okay, and the probability of success is half. Let's say probability of head is half. Okay, so if you are doing 100 coin toss, how many heads will come? 50 around, right? That's what it is. Expectation of X is 100 into half, 50. On an average, how many heads will come? 50 heads. That's what it is. Expectation of X is n into p. Variance of X is np into 1 minus p. NPQ. Okay, variance also, you know, is easy to calculate. 1 minus p is sometimes written as q. So I have told 1 npq or np into 1 minus p. Okay, so this is the distribution structure for different p and n. It's shown how the binomial distribution is binomial PMF can be plotted. Okay, for different p equals to 0.5 and n equals to 40. This is this. Okay, points or random variable. Okay, points or random variable. Let a discrete random variable X denote the number of times an event occurs in an interval of time or space. Okay, so this is mainly, it's the number of times something happens. Okay, number of vehicles passed in 1 hour at some crossing. Okay, can be modeled using points or random variable. Number of times floods are happening within last 10 years can be modeled using points or random variable. Okay, so these points or random variable has only one parameter, which is lambda parameter. It is also a discrete random variable. So the PMF goes like this: probability of capital X equals to small x is e to the power minus lambda, lambda to the power x by x factorial. This is a very peculiar distribution which has its mean as lambda and variance is same as lambda. Okay, but it's very useful. Okay, in many many applications, Poinshaw process, Poinshaw distribution is used. Okay, this is for lambda equals to 3. How this will look like? Okay, e value, you know, lambda is 3, let's say. So how does it look like? For x equals to 0, what will be the probability? X equals to 1. So it will look like this. Okay, these are discrete. Okay, you can see on the on an average, you know, around 3, these are the peaks, right? Average is 3. Remember, lambda is 3, so average is 3. So around 3 there will be peaks. After, if it is moving far from 3, probability is very less. Okay, here also there is no negative value. X runs from 0, 1 to infinity. Okay, or for all other values of x, probability is 0. This is, of course, obvious. Now let's move to continuous random variables. First one is uniform random variable. Okay, the density is uniformly distributed. Let x is a continuous random variable with the following PDF. Okay, let's say the PDF is fx is 1 by b minus a. Fx is 1 by b minus a. A lies between a and b. Everywhere else, probably fx will be 0. Okay, if x is outside this range, a and b, fx will be 0. It's not mentioned, but it's obvious. Fx is please remember, fx is density, it's not probability. Okay, probability you can calculate by integrating fx. Now, sorry. Then x is we call, if x follows this function, this PDF. So x follows uniform random variable with two parameters, a and b. Okay, uniform random variable has two parameters, a and b. Now let's example, you are in a building and have to take an elevator to reach your floor. Once you call the elevator, it will take between 0 and 40 seconds to arrive to you. Let the elevator arrives uniformly between 0 and 40 seconds after you press the button. In this case, a is 0 and b is 40. And what is the fx? Fx is 1 by 40 minus 0. It's 1 by 40. Okay. Now you can calculate all the probabilities. Different probabilities can be calculated. Let's say if I ask you what will be the probability that elevator comes in between 10 to 20 seconds. So you need to integrate 10 to, so the probability is probability of x lying between 10 to 20. So it will be the integration of fx, which is 1 by 40, from 10 to 20. Okay, integration limit will be from 10 to 20, 1 by 40 dx, whatever will be the answer, that is the answer. So in this manner, you can calculate all the probabilities like that. So what is the expectation? Expectation is very, if a and b everywhere, the density is same. So the mean will be a plus b by 2. Here, mean will be here. So please remember, mean is always in this scale. Okay, mean is always in some value of x. Okay, what is mean? If I ask you to guess, I give you a distribution and guess the best possible value of that distribution. One value you need to say, that will be the mean, right? So if I have to guess something, when the elevator will come, I will guess that it will come within 20 seconds, right? At 20 seconds, around 20 seconds, right? So something like that. So what will be the variance of x? Variance of x is b minus a whole square by 12. This also you can calculate easily. Exponential random variable is also a very interesting random variable. It is also continuous random variable. It has this PDF, fx equals to lambda into e to the power minus lambda x, where x is always positive and lambda is also positive. Exponential distribution has a parameter lambda, only one parameter. Okay, so for different lambda you will get different value. As you can see here, the exponential distribution is different for different lambdas. Okay, now usually it is time until certain event occurs. Okay, let's say within 1 hour how many telephone usually time until certain event occurs. Okay, if I say that within 1 hour how many telephone call will come, this can be modeled using Poisson distribution. Okay, so if I ask you that one telephone call has come, now next when the next telephone call will come, this time is distributed or is can be modeled using exponential random variable. So it's usually time until certain event occurs. Okay. So expectation of x is 1 by lambda, variance of x is 1 by lambda square. Okay. Normal random variable is a very important random variable, actually is the most important random variable. The name normal comes from because most of the natural phenomenon is distributed like that. That's why it's normal. Okay. So normally everything or most of the things takes this shape. Okay. Let's say height of distribution of the height of students or participants, or let's say students in a college. Okay, there will be uh, students will be in between maybe 4 feet to 6 feet. Okay, 4 feet to 6 feet, but in between 5 feet there will be peak, right? After 6 feet there will be many very small number of people. Before or around 4 feet also there will be small number of people, right? So it will look like somewhat normal distribution. Okay, so most of the things, weight also, uh, you know um, these are generally normally distributed. Let x, so the distribution form is a little bit complicated. Let x is a continuous random variable with the following PDF. Okay, this PDF is x has, now if x follows normal distribution, it has two parameters. Okay, one is mu, which is mean, another is sigma square, or sigma also you can say. Sigma square means its variance. Okay, so if you change these two parameters, the shape will change. You can see for different mu sigma square, the shape of the distribution is changing, right? Sigma square is more, variance is more. This is this curve. You see the dispersion is very high. But why it is coming down from this one? Why the height is low? Because the area should be 1, right? The total area under the curve should be 1. Now if you think of this area is also 1. But if if you stretch it, the height will come down, right? Because the area is 1. If you want to make the area in this way, so the dispersion will be smaller. If you want to make the area in this manner, stretch it, the height will be smaller, like that. So then x is a normal distribution, normal random variable. It follows, x follows normal mu sigma square. Okay, x follows normal mu sigma square, like that we write. There are two parameters. Of course, expectation of x is mu and variance of x is sigma square, as expected. You can calculate from this formula also, expectation and variance. This will be a little bit difficult calculation, but any standard probability book you can see how these are calculated. Integration is required. Okay, so till this point we only discussed probability distribution. We have 5 minutes. The next part we need to talk about regarding sampling distributions and central limit theorem. Till this part, if you have any question, you can ask. Otherwise, we'll move forward. Is it going fine? Understandable?
Yes, sir.
Yes.
Okay. Very
Sir,
good.
I have one question.
Yes. Yes.
Actually, can you give some application of Poisson distribution where we can use it?
Okay, I have not given in the slide. I mean, Poisson distribution in general. Let's say in most of the cases, it's as I said here, that it is if it is within a time frame or within a space, if you limit the space or limit the time, how many events, particular events are happening. Just like, let's say, one customer care is wants to model how many telephone calls they receive during a day. Okay, so there will be some average, and based on that, that average will be, lambda. And based on that, they can calculate the probability for a particular day having some number of phone calls. Let's say they want to, let's say average is 1,000 phone calls. Now you can find the distribution with that average lambda. Now, you know uh, you can find different probabilities for different x's. Let's say they want to find that in the next day, how many calls will come. Let's say how many, let's say what will be the probability that 500 calls will come next day. So they can find the probability in that manner. Okay, so you put x equals to 500 and find the probabilities. That manner, these are Poisson distribution can be used. Let's say in the case of disaster management also, it's highly used. Like how many droughts or how many floods, how many huge rainfalls will be there within a space, let's say within a city or within a
Specific area.
specific area. This also can be modeled using Poisson distribution.
Okay.
Okay.
Okay. Thank you, sir. Thank you.
Okay. So we can move forward, I guess. Let's see. Next is statistical inference. We need to talk about regarding sampling distributions. Okay, sample. These things are coming under inference topic. So we need to have a little bit understanding of inference before we move forward to sampling distribution. What is statistical inference? Statistical inference is you need to infer something about a huge population. Okay, let's say, for example, you want to find the average or mean salary. Okay, mean salary for Indian population. Okay, or per household income. Okay, something like that. Okay, let's say mean salary for throughout in the Indian population. What will be the mean salary or mean income, whatever you can say. So if you consider the population of India as the population, how do you do it? In general, statisticians do it this kind of solve this kind of problem by taking samples. Okay, let's say you take 1,000, 100, I don't know, depends on the population, maybe 50,000 samples, proper samples, random samples, and then you take some, you do some statistical methods, use some statistical methods to find that answer, right? Generally, if it is mean, then you do the sample mean. You take proper 50,000 samples and take the mean of those samples to find the mean income of the population. This process is not so easy. I'm crudely just mentioning because it's a sampling procedure is also very difficult for a large country like this, because there are many types of sampling process, stratified sampling, random sampling. Okay, there are different in India, there are different types of population, different types of demography. All these things needs to be considered, but in general, crudely, random sample you need to take, and you need to find some function, or you do some analysis to find the answer regarding the population, right? So this population characteristic, which is a mean income for Indian population, this is the characteristic of the population. This is called parameter. Okay. Now, you are finding sample mean also, right? So you take 50,000 sample from the Indian population. Indian population is, let's say, 150 billion, 140 billion, I don't know. 140 crores, sorry, not billion. Mm, Around 140 crores. So you take 50,000 or 1 lakh sample from that and do the sample mean. Sample mean means you take simple average of those, ask their income and take the average. This is you will get sample mean, right? This is a characteristic of a sample. So this is called statistic. So there are two things. One is characteristic of population, which is called parameter, characteristic of sample, which is called statistic. We use characteristic of sample to estimate the characteristic of population. Okay, how do we do it? That study is called statistical inference. Okay, so simply speaking, this is the thing.
Sir, exit poll and opinion poll are example of this?
Exit poll is one kind of sampling. It's not random sampling, but it's yeah, one kind of sample. And yeah, and they are also using this kind of statistical inference. So most of the time what they do in exit poll, whoever is coming out, they take their opinion. That is not random. That's why they, it's not properly done and they miss most of the time. So parameter estimation and hypothesis testing, there are two parts in statistical inference. One is called parameter estimation. The other part is called hypothesis testing. Okay. The other part is called hypothesis testing. So how they are different? They are basically two different types of inferences. Okay. Let's say this example we have shown here. Suppose that an engineer is analyzing the tensile strength of a component used in an automobile. Let's say it's a component used in a car, the strength of that component. Okay, an engineer is analyzing. So the engineer wants to estimate the mean strength of the population of components. Okay, in practice, the engineer will use some sample data to compute a number that is in some sense a reasonable value, right? So you get some sample data. So let's say the engineer wants the mean strength of the production, from a large company, a large manufacturing unit. Now, lakhs of this production happen every day. You cannot you cannot take all the components and take their mean, right? So they use some sample data and take their mean. This will be a reasonable guess. This will be a reasonable value. It's a good guess of the true population mean. What is the true population means? This is the mean strength of the population of the components. The sample mean that you get is called point estimate. Okay, this is one type of problem. Okay, you want the exact value or estimate of the mean strength. This is one kind. The previous problem also we said that you want to know what is the mean salary or mean income of the population. So you want one value, right? This is estimation problem. What is the testing problem, or what is the hypothesis testing problem? Let's say someone told you that the mean salary of India would be 10,000 per month. Now you test it. Okay, you can take samples to test that claim. The same problem is shown here also. Now let's consider different type of question. Some experts claim that the mean strength is 0.5 unit. Okay, the engineer wants to check whether the claim is true or not by using samples. Statistical hypothesis testing is the framework for solving problems of this type. Notice that there is no emphasis on estimating mean strength. Okay, we don't want to know what is mean strength. we only want to know whether it is 0.5 unit or not. Okay, we don't know whether it is some other value. Okay, so what that value is, we don't want to find out in this case. We only want to know whether that mean strength is equal to 0.5 unit or not. Okay, so the focus is on drawing conclusions about a hypothesis that is relevant to the engineering decision. So these are two types. Now we move to sampling distribution. Let me, can we have 10 minutes break or 5 minutes break, sir? Whatever is fine. I mean, this part is also not complete. We can move forward.
You can move forward if you can.
Okay, no problem. So, sampling distribution. Let's assume that we need to obtain a point estimation problem. Okay, a reasonable value of a population parameter before the data are collected. This is a very important concept. You need to understand this. Before the data are collected, the sample observations are considered as random variables. Why this is called so? Let's say I want to collect 1 lakh sample of Indian population. Okay, 1 lakh sample, 1 lakh people I am selecting. So if I select 1 lakh people, I will select certain 1 lakh people. If you select 1 lakh people, it will be different, right? All the characteristics of those samples will be different. If someone else will take 1 lakh sample, random sample from the Indian population, they will collect some, they will select some other 1 lakh people, right? So like that, this is also, these are not known. These values x1, x2, xn, these values are not known until you take the sample. So they can be considered as random variable, and these random variables are coming from the population. So any element, if it is a random sample, any unit of the population can come to the random sample. Okay, have the same every unit of the population have the same probability of being included in the sample, right? So anyone can come. We don't know. If I select, someone will come. If you select, someone else will come. So it's also random variable. So the salary x1 in this case corresponds to the salary, right? So salary of the first person, salary of the second person. These salaries will also be different. If I collect 1 lakh salary will 1 lakh different salary you will get. If you collect 1 lakh different salary you will get. Okay, their average will be different. So sample mean for me will be different, for you will be different, for someone else will be other. They can vary too much also. Okay, there may be variances in the samples also. High variances is possible. Okay, therefore any function of the observation, of the sample observation, or any statistic is also a random variable, right? So statistic is what? Statistic is the characteristic of the sample. So statistic is also a random variable. Like that, sample mean is also a random variable, correct? For example, the sample mean x bar, sample variance s square. X bar is simply calculated x1 plus x2 plus xn by n. Sample variance s square is 1 by n minus 1 summation x I minus x bar whole square. This is very simple. Okay, these are also random statistics. These are random variables. Okay, so if I collect, I will get some sample mean. If you collect some other sample mean, will get. Okay, until the sample data are collected. Before the data are collected, these are random variables. Since a statistic is a random variable, it has some probability distribution. We have talked about probability distribution now. Now statistic, that means sample mean, let's say. Sample mean has its probability distribution. We call this probability distribution of a statistic as sampling distribution. Okay, sampling distribution of statistic, or sampling distribution of mean, sample mean. The random variables, this is random sample and statistic. The random variables x1, x2 to xn are a random sample, let's say of size n. Okay, when we call it a random sample, if the xi's are independent random variables. Okay, xi's are independent, that means you are taking each sample independently, and every xi has the same probability distribution. Okay, x1 is also coming from the population, x2 is also coming from the population, xn is also coming from the population. So if your population is normally distributed, let's say, okay, let's say the distribution of the salary or income of Indian population is normally distributed. So from that normal distribution, you are collecting n number of samples. It's as simple as that. Okay, so that sample, unless that sample is collected x1, x2 to xn, all of them will have the normal distribution only, because any of them may come, right? So these are coming from normal distribution, let's say, assumption any distribution is possible. If the population distribution is normal distribution, then each of them will have normal distribution, each of them has the same probability distribution, right? A statistic is any function of the observations in a random sample that we have talked about. For example, if x1, x2 to xn is a random sample of size n, the x bar and the sample variance s square and the sample standard deviation s, these are all statistics. Since a statistic is a random variable, it has probability distribution. The probability distribution of a statistic is called sampling distribution. For example, the probability distribution of x bar is called the sampling distribution of the sample mean. Okay, probability distribution of x bar. The sampling distribution of a statistic depends on the distribution of the population. That's what we talked about. The size of the sample is also very important, that we'll see. And the method of sample selection, random sample is generally preferred because it's easy. It's easy for us to make inferences using random sample. The probabilities are same and all, so it's easy to handle. Suppose sampling distribution of sample mean. Suppose that a random sample of size n is taken from a normal population with mean mu and variance sigma square. This is the question. Okay, suppose that you are taking a random sample of size n, x1, x2 to xn, from a normal population with mean mu and variance sigma square. Now, each observation in this sample, say x1, x2 to xn, is a normally distributed, and they are independently distributed also. x1 is normal distributed, x2 is independent of x1 and normally distributed, xn is also normally distributed independent of them, other random samples. Okay, with mean mu and variance sigma square. Okay, normally distributed with mean mu and variance sigma square. You remember normal distribution has two parameters, is defined by two parameters. One is mu and variance is sigma. Another is sigma square variance. So now each observation is this, let's say. Now what will be the sampling distribution of the sample mean x bar? This is the question. If you take n number of random sample from a normal distribution with mean mu and variance sigma square, now you average them. What will be the average, the distribution of the average? Okay, what do you think? What will be the mean? What will be the distribution? The distribution of x bar. What will be the mean of x bar? What will be the variance of x bar?
Mean will be same because it's a constant.
Okay, mean will be mu only.
Yeah, but because x bar is a constant, no?
X bar is random variable here because these are random sample.
Yeah, but mean of the random variables is x bar.
No, mean of the random variable is not X bar. Ever only x1 plus x2 plus xn by n is X bar. Okay,
Yeah, that's what
this is not
it is
X.
called mean.
So it will be mean of all samples.
Yeah, just one clarification here. Expectation of x1 is mu. Okay, expectation of x1 is mu, and the if you take average of the random samples, you will get another random variable. Okay,
Yes, yes.
because all of them are random variable. Let's say I'm taking 10 samples. Okay, I average them.
So
Okay, I'm
x bar
getting one.
is average of all mu's.
X bar is the
Average of all mu's.
no. X bar is a random sample, a
Okay.
random variable which denotes that it is the average of the random sample. Let's say I am taking 10 samples, I am making an average. Let's say that average is 5. You are taking 10 samples, you are making an average of that sample, you will get 6, let's say. So what will be the distribution of that averages? Okay, I will get a sample average 5, you will get a sample average 6, someone else will get 5.5, someone else will get 7. So there will be X bar will also take different values, right? So that then X bar will also have probabilities of taking different values.
Okay. Okay.
That
Okay.
means X bar is a random variable, it has a distribution, but its mean will be mu only. Okay,
Okay. Okay.
mean will be mu because it can be, it's easily derived. I have not derived here. Expectation of x1 is mu, expectation of x2 is mu, expectation of xn is mu. So if you take x1 plus x2 plus xn by n, expectation of this value will also be mu. Okay, because expectation is linear, it's very simple. As linear functions, and the distribution of x bar will be normal distribution. Okay, as we have said, uh, as linear function of independent normally distributed random variables are also normally distributed. Linear function means x bar is x1 plus x2 plus xn by n. This is a simple linear function. Okay, so x1 is normally distributed, x2 is normally distributed, xn is normally distributed. So their linear function will also be normally distributed. This is a particular property of normal distribution. Okay, so it does not happen with all the distributions, all the random variables. It happens with normal distribution. Okay, the sample mean x bar has a normal distribution with parameters mu. It's also very simple. If its mean will be always mu. Expectation of x bar is nothing but expectation of x1 plus expectation of x2 plus expectation of xn by n. So expectation of x1 is mu, expectation of x2 is mu, expectation of xn is mu. So it will be n mu by n. So it will be mu. Okay. Variance will be smaller than sigma square. Variance will be reduced. Okay, this also can be explained. Variance formula, using variance formula I have not shown. You can check it in any probability book, you will get it. Okay, variance is reduced. It's not x1 x2 to xn. X1's variance is sigma square. Now this x bar's variance is sigma square by n. So it is, as n is increased, the variance will get reduced. Okay, so if we are now this is only, we are talking about samples we have taken from normal population. Okay, normal distribution with mean mu and variance sigma square. What happens? Population distribution is unknown. Population is not normal. It's possible that the income of Indian population is not normal. Okay, it may be some other thing. In that case, if we are sampling from population that has an unknown probability distribution, what will be the sampling distribution of the sample mean x bar? Okay, this question is not easy. to answer. To answer this question, we need one more theorem, which is called central limit theorem. Okay, if it talks about large samples, okay, if x1 x2 to xn is a random sample of size n, okay, if x1 x2 to xn is a random sample of size n taken from a population, either finite or infinite, whatever it is, with mean mu, that population with the distribution we don't know, but its mean is mu and variance is finite, which is sigma square, finite variance. And if x bar is the sample mean, simple sample mean, the limiting form of the distribution of x bar, limiting form as n tends to infinity. So you are taking large samples and taking the average of the samples. Okay, x bar is the sample average of large samples. Okay, in that limiting form, the distribution of x bar will be normal with mean mu and variance sigma square by n. Okay, so what it says is, even if you are not taking the sample from a population which is normal, okay, you are not taking from a normal population, okay, you are not taking sample from a normal population. If you take large number of samples and if you take their average, the distribution of that sample average, sample mean, will be normal. Okay, this is a very interesting property. It can be proved also. It's easily any probability book you can find it, the proof. The normal distribution will have mean mu and variance sigma square n. This sigma square by n, okay, these phenomena can be explained using the following example. Let's see the example to understand clearly what is happening here. Consider the distribution obtained for throws of a single six-sided paired die. Okay, the distribution for throws of a single six-sided paired die will be, six side means there will be six side. So 1, 2, 3, 4, 5, 6. The probabilities are equal 1 by 6. Any side can come with equal probability, right? So for 1, 2, 4, 3, 4, 5, 6, the probabilities are equal 1 by 6. Now, let's consider that you have such six-sided dice, lakhs, infinite number of such six-sided dice. Okay, you want to take some samples out of them. You are taking some samples, let's say 2 samples you have taken. Check the distribution of average scores obtained when tossing 2, 3, 4, 5, 2, 3, 5 and 10 dice. Okay, let's say only 2 dice you have taken. Now you take out of those infinite number of dice, you take 2 dice and throw them and measure the die outcome. Let's say 3 and 4 has come. So your sample average is 3.5, right? 3 plus 4 by 2. Now this has happened once. You take another 2 and then again throw. Sometimes you will get 6 and 1. So it will again come 3.5. Sometimes you will get 4 and 5. You will get 4.5 average. Sometimes you will get 2.3, some 2.5 or something else. Okay, like that you will get, if you do the trial 1,000 times, thousands of averages you will get. If you plot them, you will get a distribution. That distribution is for n equals to 2 samples, average of n equals to 2. If you take 3 such dice, and do continuous this kind of trials and take the average, note it down. For 1,000 times you do that. Okay, take the average 1,000 times, 1,000 averages you will get, and just plot the histogram. You will get some distribution, right? So that distribution is your n equals to 3 sample mean, right? As you increase For n equals to 10, the distribution will look like this. Only for 10. If you do more than 10, 1000, 100, 500, 1000, it will look like exact normal curve. Okay. And this is very interesting because the distribution of population is only a discrete distribution, and their sample average is coming as continuous distribution, right? Normal distribution is continuous distribution. This is a very interesting phenomena. Anyway, we'll not spend too much time about it because we have other things, which is one sampling distribution example I have given, which is standard normal distribution or Z distribution. There are many such sampling distributions like T distribution. You have heard of T test. You have heard of maybe chi-square test. You have heard of F test. Many tests are there. We'll only consider Z test here. Z test is widely used, okay, and very it's not too difficult to understand. Okay, let's see. For Z test, you need to understand Z distribution, which is a sampling distribution. So Z distribution is very simple. It's a standard normal distribution. It's called standard normal distribution. It's a normal distribution where mean is 0 and variance is 1, or standard deviation is 1. Okay. One property of normal distribution is if X is the normally distributed random variable, normal mu sigma square, okay, then the new if you form a random variable in this manner, X minus its mean by its standard deviation, okay, this will be another random variable, right? Because X minus one constant by one constant, it will be another random variable. This random variable follows standard normal distribution n01, okay, where mu is 0 and sigma square is 1. So this is a very interesting property. Using that property, many things can be done. The random variable that possesses the standard normal distribution is denoted by Z, and its scores are called Z scores or Z values. Okay, so Z distribution is taking Z values with different, probability density, right? With different density. So if you see this distribution, this is the density of standard normal distribution, which is 1 by root 2 pi e to the power minus half x square. If you remember the formula, 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. There we have only put mu equals to 0, sigma square is 1. You got this equation. Now if you plot it, it will look like this. Now different probabilities you can find easily. Let's say I want to find Z score is 1. What will be the probability? Or let's say Z score is minus 1. What will be the probability of capital Z or standard normal variable Z less than minus 1? That will be this area, minus infinity to 1, whatever under the curve is coming, this area. If I want from minus infinity to 3, whatever full area is there till here, this will come. This is the value, probability, right? Under area, the total probability under the curve will be 1. We all know. Now all these small probabilities are calculated already, and it is given by the statisticians as Z tables. Okay. Now Z is a symmetric curve. You see, Z, any normal distribution is symmetric bell curve. The symmetric about its mean. Now Z distribution is symmetric about 0. That means the area in the left side of 0 is 0.5. The right side of 0 is also 0.5, right? Total is 1. So, here using Z table, you can calculate different probabilities. What is the probability cumulative probability is mentioned here. This is Z. Okay, so Z value is here. Let's say you want to find Z less than -3. Z less than -3.000 is 0.0013. The probability will be 0.0013. What will be Z less than 0? As we are talking about, Z less than 0 will be 0.5. Like that. All the probabilities can be calculated. Okay. So end of this slide, we are going to
One question.
hypothesis testing. Before that, you can take question, of course. Yeah. Yes. Please go ahead.
In that
If you
Z
have
score
question.
table, you referred first column,
Yeah.
but there are more than one columns, no? 6 to 7 columns.
These are Z values. Okay. These are Z values. And these are probabilities. These are probabilities. Okay. For this Z value, let's say you want to find probability of capital Z less than -3.45. How do you calculate? -3.4 is here and 0.5 is here. Okay. So if you consider the -3.45, the probability is this.
Okay, sir.
0.0003.
Yes.
Okay. Yeah.
Sir,
Yeah.
is there any sample size restriction there for using this Z test?
For central, for using central limit theorem is generally we statisticians use the n greater than 40 number of samples should be more than 40. Then we can use central limit theorem. Okay. In that case, what I mean to say is that population distribution is unknown. In that case, if the sample size is more than 40, then the distribution of the sample average goes to normal distribution, and from there you can get Z distribution. Okay. Otherwise, if the population itself is normal, there is no restriction in the sample. Okay. This the population distribution is itself is normal. You are collecting data from normal distribution, sample data. Okay. So always the sample average will be normally distributed.
Okay.
Whatever, even if you take 2 samples. Okay. Central limit theorem is generally applied when the population is non-normal. Okay. In that case, you need to take at least 40 samples.
Okay.
Okay. So I'll just take 1 or 2 minutes break. So I'll just some water. Okay. Let's start again.
Sir, I have one question.
Yes.
So, yeah, so I have read in some books that when we have sample less than 30, we go for T test. And if it is more than 30, then we go for Z test. So, what would be the reason?
So that is in a different context. It's not all. Yeah. So T test can be used when sample population variance is unknown. We'll come to this part. We have slides for that. Okay.
Okay, sir.
let's move to hypothesis testing. In many situations, what is, test of hypothesis? In many situations, a different type of problem is of interest, different type other than estimation problem. That's what we are meaning here. There are two competing claims about the value of a parameter. Parameter means population characteristic, if you remember. Population characteristic. Let's say you want to estimate the mean salary or mean income of Indian population. That is your parameter. Okay. So you want two competing claims about the value of a parameter, and the engineer must determine which claim is correct. In that case, test of hypothesis is used. One case study example, this example only we are following throughout the slides. Suppose that an engineer is designing an air crew escape system through which air crews can escape in case of emergency, that consists of an ejection seat, okay, one seat to be ejected, and a rocket motor that powers that seat. The rocket motor contains a propellant, and in order for the ejection seat to function properly, the propellant should have a mean burning rate of 50 centimeter per second. Okay, this is the condition. The propellant should have a mean burning rate of 50 centimeter per second. If the burning rate is too low, some problem is there. Higher burning rates will induce other problems. Okay, so it should be 50 centimeter per second. Okay, so the practical engineering question that must be answered is now, does the mean burning rate of the propellant equal 50 centimeter per second, or is it some other value, either higher or lower, whatever it is possible? This type of question can be answered using a statistical technique called hypothesis testing. Now, we are not going into this engineering problem in detail. Our interest is to test whether mu, which is mean burning rate, is equal to 50 centimeter per second or not. This is how do we solve it, is called hypothesis testing. Statistical hypothesis, what is it? Statistical hypothesis is a statement about the parameters of one or more populations. Okay, it may be more populations, two populations also, or one population. In this case, it is only one population we are talking about. So null hypothesis and alternate hypothesis, sometimes it's called alternative hypothesis. Okay, what are they? Null hypothesis is something like this: H naught is null hypothesis, which is mu equal to 50 centimeters per second. If we consider the previous example, okay, our alternative hypothesis is H1, which is mu not equal to 50 centimeters per second. Okay, most of the time, in general, null hypothesis is kind of an equality. Okay, and alternative hypothesis, most of the time it is an inequality. Sometimes it's not equal, sometimes it's unequal. Let's say it's possible that mu less than 50 we are testing, or mu greater than 50 we are testing. So if you are testing alternative hypothesis mu not equal to 50, so it can be both sides, right? It can be 48, it can be 52, or it can be 41, it can be 59. So anything is possible, right? Both sides. It's called two-sided. It's called two-sided alternative hypothesis. One-sided alternative hypothesis is also there. We have not considered in this. In this slides. Is just mu equals to 50 against mu greater than 50. Okay, or mu less than 50. We are testing whether mu is less or it is equal. Okay. Now, test of hypothesis procedure. What is the procedure? A procedure leading to a decision about a particular hypothesis is called a test of hypothesis. Hypothesis testing procedures rely on using the information in a random sample. Now you have collected a random sample from the population of interest. Okay. If this information that you have collected from the random sample is consistent with the hypothesis, we will not reject the hypothesis. Okay. So you are collecting a sample from a population, you decide some statistic, some characteristic, some information you get. That information should be in line with the hypothesis. Then only we will not reject the hypothesis. If it is inconsistent with the hypothesis, then we will conclude that the hypothesis is false, or we reject the null hypothesis, something like that. We emphasize that. So by that, what we mean is that, okay, we'll explain here only with this example. We emphasize that the truth or falsity of a particular hypothesis can never be known with certainty. Okay, whether mean burning rate is 50 or not, we will never know, because it's a population. We are only collecting sample, and the hypothesis that we are testing is fully based on the sample characteristics, right? Unless we can examine the entire population, this is usually impossible in most practical situations. Okay. This is usually impossible in most practical situations. That's why errors are coming, right? So errors will come. We'll talk about the errors also. Testing the hypothesis involves taking a random sample. It's very simple. You take a random sample, compute a test statistic from the sample data, and then use the test statistic to make a decision about the null hypothesis. Case study example: consider the propellant burning rate problem. A null hypothesis is this: mu equals to 50, against the alternative hypothesis is mu not equal to 50. Now suppose that a sample of n equals to 10 specimens is tested. You have tested it. Tested 10 specimens, and the sample mean burning rate x bar. Sample from those 10 samples, you calculate the mean burning rate, which is small x bar. See, we have written here small x bar. This should also be small x bar. Okay, small x bar means the calculated average. You have got the value, that is small x bar, is observed value. The sample mean is an estimate of the true population mean mu. Okay, the sample mean is a very good estimate, actually unbiased estimator of true population mean mu. Okay, so we can intuitively say that a value of the sample mean x bar that falls close to the hypothesized value of mu equals to 50 centimeters per second does not conflict with the null hypothesis, right? So if it is around 50, your sample mean around 50, that how far is that around, that will decide later. But let's say it's consistent, right? Around 50, close to 50. So it is consistent with the null hypothesis then. So we will not reject null hypothesis. On the other hand, a sample mean that is considerably different from 50 centimeters per second, it is evidence in support of alternative hypothesis H1, which is, let's say you collect a sample of 10 samples and you calculate the sample mean burning rate, which is, let's say, 38 centimeters. It's not really supporting the null hypothesis, right? So you should reject the alternative hypothesis, reject the null hypothesis, and in favor of alternative hypothesis. Thus, the sample mean is the test statistic in this case. Okay, the test statistic that you are using here is sample mean. the sample mean now can take on many different values. Suppose if X bar, your sample mean, is in between 48.5 to 51.5, if this comes, we decide not to reject the null hypothesis. Okay, if because it is close to 50, X bar is close to 50, we decide this range. How we decide that will come later. Okay, this is the test. That is the point. How we are deciding how far we allow. Okay, how far we allow the acceptance region. This is called acceptance region. Okay, because we are accepting null hypothesis, right? We fail to reject null hypothesis. X bar lies between this is the acceptance region. X bar out of this region is critical region where we will reject the null hypothesis in favor of alternative hypothesis because it is not in line with the hypothesis, null hypothesis, right? So here we have shown the X bar line. Here, if X bar falls here, 48.5 to 51.5, we will not reject H naught. That means mu is 50 centimeter per second. If it comes here 51.5 more than that, if X bar is more than 51.5, we will reject H naught. If X bar is less than 48.5, we will reject H naught. Okay, so these are critical region. This region is critical region. This is acceptance region. Okay, it is customary to state conclusions relative to the null hypothesis H naught. Okay, relative to the null hypothesis, like that we say that we accept null, we fail to reject null hypothesis, or we say that we reject null hypothesis. Okay, something like that we say. Okay, it's always in terms of null hypothesis. So there are two types of error that can happen in the process. Okay, this decision procedure can lead to either of two wrong conclusions. For example, the true mean burning rate of the propellant could be equal to 50 centimeter. True mean, that means population mean. Okay, mu is actually 50 centimeters per second, let's say, but your X bar falls into critical region. It's possible that you have collected a sample and your sample average is 45. Then you will reject null hypothesis. But actually mu is mu is 50 centimeter per second. Somehow the sample came like that. You got some sample average 45 or 47, something like that. So you will reject null hypothesis, which is not right. That is the error you are making. That error is called type 1 error. So what is type 1 error? Rejecting the null hypothesis H naught when it is true, when it is actually true, okay, is defined as a type 1 error. Now, we never know what is true, okay, but we can calculate the probabilities. Probability of making type 1 error can be calculated. Probability of type 1 error is alpha. It is probability of rejecting H naught when H naught is true. Okay, significant, it's also called significance level or the alpha error or the size of the test. Okay, so alpha is very important. Actually, we control alpha only in any hypothesis testing. You will see that alpha is 0.05. That is type 1 error. Okay, there is another type of error which is type 2 error. Failing to reject the null hypothesis when it is false. Okay, let's say burning rate, mean burning rate, true mean burning rate is actually different from 50. It's not 50, but your sample mean comes under the critical acceptance region. Let's say your sample mean came 48.9, so you will accept the null hypothesis, but actually you should reject because the the actual thing is that population mean is not 50. So in this case also, one error you are making, that is called type 2 error. Okay, generally the analyst controls the type 1 error probability alpha because of many reasons that we are not going in detail. When he or she selects the critical values. What is critical value? Critical value is this 48.5. Okay, what is critical value? 48.5, 51.5, right? So these are the region these are the values that decide the regions, boundaries of the regions, critical regions and acceptance regions. These are critical values. These critical values you need to decide. These are decided based on alpha. Okay? Because we can control the probability of making a type 1 error, a logical question is what value should be used. Okay, what value we could, it should be of course very small. What small value we can take? The general idea is widely accepted procedure is 0.05 we should take. Sometimes we take 0.01 also. Okay, one way to report the results of a hypothesis test is to state the null hypothesis was or was not rejected at a specified alpha value. Okay, let's say for alpha equals to 0.05, your hypothesis is rejected. It's possible that for different alpha value it is accepted also. Okay, depends on the error you are making. Okay, you are allowing. Okay, this is called fixed significance level testing. So you have some fixed significance level, which is, let's say, alpha equals to 0.05. Based on that, you decide some critical values, and you decide the critical region, you decide the acceptance region. If your test statistic falls in the acceptance region, you accept the null hypothesis. If your test statistic falls in the rejection region or critical region, you will reject the null hypothesis. This is very simple, fixed significance level testing. Another testing approach is there, which is called p-value approach. The calculation of p-value, we are not going into the detail. Simply, we are saying what is p-value. P-value is the smallest level of significance. Smallest level of significance. Okay, smallest significance level for smallest alpha that would lead to rejection of the null hypothesis H0 with the given data. Okay, so fixed significance levels have some disadvantages. So sometimes p-value is also p-value. Nowadays, all the softwares are giving p-value only, and it's very easy to decide whether you are rejecting or accepting based on p-value, because if p-value is less than alpha, you are rejecting null hypothesis. If p-value is greater than alpha, you fail to reject the null hypothesis. It's very simple, because p-value is the smallest level of significance that would lead to a rejection of the null hypothesis. So alpha, if your alpha is higher than that p-value, so you will reject the null hypothesis. Okay, in this manner, consider the previous example. Let the observed sample mean is, if the sample you have taken and the observed sample mean is 51.3 centimeter per second, and you calculate the p-value, you get p-value 0.038. Compared to the standard significance level 0.05, our observed p-value is smaller. So if we were using a fixed level of significance, fixed significance level of 0.05, the null hypothesis would be rejected, right? In fact, the null hypothesis H0 mu equals to 50 would be rejected at any significance level greater than or equals to 0.038, because that's the, this is the definition. Operationally, once a p-value is computed, we typically compare it with the predefined significance level to make a decision. Often this predefined significance level is 0.05. However, in presenting results and conclusion, it is standard practice to report the observed p-value. Okay, because if you don't report the p-value, we will not know whether it is just in the boundary. Okay, your sample mean or test statistic fall, let's say p value is 0.049. Okay, still you will reject the null hypothesis, right? Because it is less than 0.05, but it is in the boundary, so it's very close. So experimenter will know that our sample mean or sample whatever statistic fail very close, right? If you don't report the p value, people will never know. Only critical values you will find, and you will reject the null hypothesis or accept the null hypothesis, something like that. P value is, that's why it's important. Most of the softwares now gives p value. So the technique is that p value you can calculate also. It's easily using probability. And any inference book you will find, it's not difficult at all. P value calculation in hand also you can do, but softwares give it readily, so there is no problem. So if you get the p value, compare it with the significance level 0.05. In this case, if it is less than 0.05, you just reject the null hypothesis. If it is more than 0.05, you accept the null hypothesis. Okay, general procedure for hypothesis tests. Use of the following sequence of tests are applying hypothesis testing methodology is recommended. Parameter of interest, you need to find the parameter from the problem context, identify the parameter of interest. In the last case it was mu, right? Null hypothesis, you state the null hypothesis H0, you state the alternative hypothesis H1. Test statistic, determine an appropriate test statistic. Okay, test statistic may be sample mean or something, some function of sample mean, that we'll see. Reject H0 if state the rejection criteria. Okay, we call this step reject H0 if. Okay, so you will reject H0 if this happens. State that criteria. Computations, compute any necessary sample quantities, substitute these into the equation for the test statistic and compute that value. You need to draw conclusion based on H0. Okay, H0 is rejected or you fail to reject H0, something like that. We are considering one case here. We'll talk about in detail how you test the mean of a normal distribution where variance is unknown. Okay, so the population is normal here, variance is variance is known. So population variance is known, your population distribution is normal. How do you test the mean? Okay, this is also a two-sided test. H0 is mu equals to mu naught against alternative hypothesis mu not equal to mu naught. Okay, where mu naught is a specified constant. Let's say mu naught is 1 or 50, whatever it is. Okay, it's a constant. So please remember the assumption here. Assumption is population distribution is normal and variance is known. Variance is sigma square. Okay, if the variance is unknown, then some other kind of strategy we need to follow. Now we have the random sample x1, x2 to xn from a normal population. Now, if the null hypothesis is true, this is very important. If the null hypothesis is true, that means mean is mu naught. Okay, then x bar has a normal distribution with parameters mu naught and sigma square by n, because otherwise x bar is generally x1, x2 to xn. If it is coming from normal mu sigma square, x bar will have normal distribution. We have seen this with mean mu and variance sigma square by n. Now here we are considering the null hypothesis is true, so mu is mu naught. So x bar will have normal distribution with mu naught and sigma square by n, right? Variance. Normal distribution with mean mu naught and variance sigma square by n. Now we can calculate p value or construct a critical region based on the computed value of the sample mean x bar. Okay, we can find for different values of X bar, we will decide whether we will reject or will accept the null hypothesis. Another useful or more easier way is to standardize the sample mean. What is standardization? Is just subtracting X bar minus its mean by its standard deviation. Okay, this is called standardization. Now, if X bar is a normal distribution with mean mu naught and variance sigma square by n, then Z naught, which is X bar minus mu naught by sigma by root n, will follow Z distribution, standard normal distribution. This is a property that we have talked about before also. Okay, so Z naught should follow standard normal distribution. Standard normal means its mean will be 0 and variance will be 1. The observed value of Z naught, this random variable observed value, once you collect one sample, you will get X bar, small X bar value. Minus mu naught by sigma by root n will give you the observed Z naught. Correct? Now, if this Z naught is close to 0, that means X bar is close to mu naught, right? If Z naught is close to 0, that means it is possible that mu is close to mu naught. It's possible that null hypothesis is true. If Z naught is very far from 0, we may reject null hypothesis, right? So all we have to do is to determine where to place the critical regions for the two-sided alternative hypothesis. Now, if H naught, null hypothesis mu equals to mu naught is true, the probability is 1 minus alpha that test statistic Z naught falls between minus Z alpha by 2 and Z alpha by 2. Okay, so this is, let's say this is the distribution of Z naught. Okay, this is the distribution of Z naught. This is a standard normal distribution. Now this is, its mean is 0. So Z scores are this. These are Z scores. We write like this: Z alpha by 2 minus Z alpha by 2. Less than that, it will be, the area is alpha by 2. Okay, this area will be alpha by 2. Now this will be for different alpha. This Z will be different. Okay, let's say if you take 0.05, this area will be 0.025. This area will be 0.025. You will get Z value as 1.96. Okay, minus 1.96. Here will be 1.96. You can see this from the previous Z table also. Okay, what is the value of minus 0.0 minus 1 point minus 1 point, you see, minus 1.9. This is Z score, right? Minus 1.9, and you come here 0.06, 1.9, 0.06. You see the probability 0.025. So minus 1.9, 0.06, that gives you minus 1.96, 0.0250. So this area less than minus 0.19, minus 1.96 gives you the 0.025 area value, right? So that's what it is. So if it is alpha equals to 0.05, it will be minus this area, this value will be minus 1.96, and as this is symmetric curve, this Z alpha by 2 will also be 1.96, right? So you can calculate for different alpha these Z scores. Note that the probability is alpha, the probability of acceptance region, you know, this part is alpha, right? This part is 1 minus alpha, right? This acceptance region, this critical region are divided into two regions here, alpha by 2 and alpha by 2, because it is a two-tailed test. Okay, even if your test statistic falls here, you will reject fall here, you will reject. If it is too far from 0, that's what we are talking about. If Z value is too far from 0, both sides, you will reject, right? Because this Z naught is too far from 0 means X bar is too far from mu naught, right? So null hypothesis mu equals to mu naught may not be true. So that's what it is. Now, depending on alpha value, you will decide these critical regions easily. And if you will reject null hypothesis, if your test statistic falls here or here, you will accept the null hypothesis if it falls here. Let's directly go to the this example to see, because we are already moving ahead of time. Let's consider this example that talks about explaining the details that we have seen. Air crew escape systems are powered by solid propellant. The burning rate of this propellant is an important product characteristic. Specifications require that the mean burning rate must be 50 centimeters. We know that the standard deviation of burning rate is sigma, that is sigma is known. Sigma equals to 2 centimeters per second. Also, the assumption is normal, okay? Population is normal. The experimenter decides to specify a type 1 error probability or significance level alpha equals to 0.05 and selects a random sample of n equals to 25, okay? So your n equals to 25 and obtain a sample average burning rate of 51.3, let's say, centimeters per second. What conclusion should be drawn? Now we may solve this problem by following this 7-step procedure. Mu is the parameter of interest here. This is your null hypothesis, mu equals to 50 against mu not equals to 50. What else is known? Sigma is 2, n is 25, alpha is 0.05, X bar observed sample mean is 51.3. What is your test statistic? We have talked about it. Test statistic is this. Z naught is X bar minus mu naught by sigma by root n. Now you reject H naught if the p-value is less than 0.05, or you use this fixed significance level test. The boundaries of the critical region would be Z 0.025 1.96 and minus Z 0.025 minus 1.96. So you will accept if your this Z naught value, if you will accept if your this Z naught value will be in between minus 1.96 to 1.96, right? So this is acceptance region, you remember. So this is minus 1.96, this is 1.96. You will accept if your Z naught value comes here. What is Z naught value? X bar is 51.3, sigma is 2, Z naught is X bar minus mu naught, X bar minus mu naught, that is mu naught is 50. So mu naught by sigma by root n, right? X bar minus mu naught by sigma by root n. If you calculate this, Z naught will come 3.25, which is in the rejection region, right? Because 1.96 is here, it's more than 1.96, somewhere here 3.25, right? So you will reject. If you calculate the p-value also, it will come 0.00212. In that case also you are rejecting because it is less than alpha, less than 0.05, you will reject. So in this simple manner you can test simple hypothesis do hypothesis testing. What you need to do, you just need to form the test statistic and the critical region. Here in this case, critical region lies between minus 1.96 and 1.96. Please remember this. It depends on alpha. If you change alpha as 0.01, this value will change. Okay, it will come here somewhere. Okay, because alpha by 2 is 0.01, that means 0.005 in that case. Okay, you need to find that alpha corresponding Z alpha by 2 value. Okay, so in that manner you should change this. Now this example or the procedure that we talked about, what is the practical interpretation of this, the final decision? We conclude that the mean burning rate differs from 50 centimeters per second based on a sample of 25 measurements. Okay, this is how we can conclude. And also we have assumed here that the population is normal. What happens the population is non-normal? What happens if the population, if your sigma square is unknown? So there we use large sample test. Okay, if the population is non-normal, we have developed this procedure for considering normality, and sigma square is known. In many, if not most practical situations, sigma square will be unknown. Variance, population variance is not possible to know in many situations. Furthermore, we may not be certain that the population is normal. That also we don't know. In these situations, if n is large, this is a very important point. If n is large, that is n greater than 40, large sample is taken, the sample standard deviation S can be substituted for sigma. Okay, so the moment the thing that we were doing, x bar minus mu naught by sigma by root n, if sigma is unknown, you replace by sample standard deviation S. Sample mean, you know, sample standard deviation also you can calculate from the sample values. But then this distribution, will it be Z? Will it be P? But if it is normal distribution, then x bar minus mu naught by x bar minus mu naught by S by root n will follow T distribution if, you know, x bar is normal or the population is normal. It will not be T if the population is non-normal. If it is large sample, we can use the central limit theorem to say that x bar minus mu naught by S by root n follows normal distribution if the sample is large, you know, large sample is taken, n is greater than 40. Okay, in that case we can use the same procedure. If the sample is, you know, large, assumption of normality is not required. Z naught in any way will be distributed as normal distribution because of central limit theorem. Okay, if the population is non-normal, you know, if the population is non-normal, or if the population is normal, variance is unknown, that then in that case you can use T distribution. Okay, sigma will be replaced by S, and this distribution, Z naught's distribution, will be T, n minus 1. T with, it has one parameter which is n minus 1. Okay, degrees of freedom parameter. So these are few cases. There are many other cases other than this, because, you know, there may be two populations. Okay, you are comparing mean of two populations. Okay, mean, you know, mean salary of Andhra Pradesh, how it is, whether it is same as mean salary of Tamil Nadu. Okay, mean income of Tamil Nadu. This type of problems also can be formed and can be, you know, solved using hypothesis testing. Variance also can be, you know, the you know, variance, population variance is also another parameter, right? So you can decide regarding population variance also. Then you need to use chi-square test. That is another test. Okay, so these types of many tests are there. A very good book regarding this is Montgomery, from where it is all the, you know, slide materials I have taken. This is applied engineers, you know, probability for applied probability for engineers, or something like that is the name of the book. I think it is Applied Statistics and Probability for Engineers. Okay, this is the 7th edition Montgomery book, where if for all types of hypothesis problems have been discussed. Okay, if you have any question, please go ahead. We have taken more time. Sorry.
Any questions? Quick questions. We are running out of time. Any quick question can be asked.
Was it understandable? Is it helpful? Or
Yes, sir. Yes.
Yes, sir. It is useful. Right?
Yes, sir, it is.
okay,
But we will.
Sir, that Z value is depends on that sigma value variance.
Z value means Z naught?
No, sir. That you show that Z value is 1.96.
Yeah.
Yeah. So at that time we consider significance level as 0.05. No?
No, that value is dependent only on alpha. No? You are only considering this is we are calculating from the Z table.
Z table. Okay.
Yeah.
Okay.
Z table only if you give alpha or whatever probability value you will give, you can get the corresponding Z score.
Means if our problem change, that Z value will means that value will also change. No? Means,
Yes. Alpha, if you change, the Z value will change. Yeah.
we will calculate Z value and then we refer that table.
Correct.
Yeah. Okay.
Okay.
So with this, let us thank Professor Mainak Thakur for a wonderful lecture on the subject. So now we will move on to the next talk, which is on human values by Mrs. Kranti Y. To introduce Mrs. Kranti Y, she is from Bangalore. She is a state coordinator of the Art of Living Foundation, founded by the Gurudev Sri Sri Ravi Shankar ji. She is a chartered accountant by education, and she is teaching Art of Living programs for more than 11 years to thousands of students, directors, bureaucrats, doctors, politicians, so on. She is passionate to see and to bring smile on each and everyone's face to lead a stress-free and happy life. So now the platform is for you, ma'am.
Why?
Thank you, sir. Hello, everyone.
Hello, madam. Yeah.
Hello, ma'am.
So, after a technical session, it's always good to have one non-technical session, that too on human values, because human values play a very important role in each and everyone's life. A complete human being is one who adopts teamwork from Japanese, precision from Germans, marketing techniques from Americans, and human values from Indians, said renowned spiritual leader and founder of the Art of Living Foundation, Gurudev Sri Sri Ravi Shankar ji. Human values play a significant role in Indian society. Human values are social and ethical norms common to all cultures and societies as well as religions. They represent a melding of social progress, justice, and spiritual growth. Human values can be a deep caring for all life, a responsible attitude towards the planet, non-violence, compassion and love, friendliness, generosity and sharing, integrity, honesty and sincerity, moderation of one's activity, service, commitment and responsibility, peace, contentment, and enthusiasm. See, when we go to any small village in India, we can find human values are embedded deep inside every nerve of the rural country. It is necessary to preserve these values, which are slowly evaporating from urban India. We have diluted our own system due to anger and greediness. There can be no development until and unless certain values are restored. There is a need to uphold a strong set of values consisting of love, compassion, and dignity, which is the need of the hour. Human values can take you from a state of dependency to total responsibility and carve out a responsible citizen. People identify themselves with limited characteristics such as gender, race, caste, religion, nationality, forgetting their basic identity as part of the universal spirit. These limited identities lead to conflict in one's personal level and also globally. Every individual is much more than the sum of all these limited identifications. The highest identification we can make is that we are part of the one divinity and we are members of one human family. In divine creation, the whole of the human race is united. Along with the proper identification of our true nature, we need to return to the values that are the essence of all major traditions. It's not that we are not aware of the human values, but due to the present lifestyle in this competitive world, we are not giving that much importance to human values. But human spirit can be uplifted through human values. For this, we need to spend a little bit of our valuable time to dive deep within us so that we can awaken ourselves and reinstill human values. As faculty members, you have a very big responsibility because students learn 50% of the human values from their parents and the rest 50% from their teachers. Hope everyone agrees to that. They observe everything that you do and they pick up on it. When you are calm and when you are composed, then they observe that and they imbibe these qualities in their life. Basic human values needs to be encouraged in the classroom. Human psychology or the human nature is very similar to the atomic structure. Like in an atom, the central part of the atom is positive, a proton. The electrons or the negative charge is on the periphery. Any negativity you find in a student is on the periphery. Negativity is not the real nature of the student. With loving attention and care, you can bring out the positive human values in the student. We have to teach them how important it is to have the sense of belongingness. This sense of belongingness comes only when the mind is calm and clear. Here, meditation plays a very, very important role. When when we empty ourselves through meditation, we can let go of all the negative feelings and can recognize the human values which are deep rooted within us. So it's very important to do a little bit, to spare a little bit of time and do some meditation so that it clears all the negative feelings, negative thoughts within us, and whatever the human values which we have learned from our childhood and which are already deep rooted within our consciousness can be exhibited and we can transform the whole society. So, shall we do a short meditation now? Yes. And it's always good to do meditation during this time because this is the time where we wind off everything and our consciousness will be in a deep relaxing state. Normally, often people think that meditation means concentration, but it's not so. Meditation is opposite of concentration. Meditation is deconcentration. Effort is the key to the body, but effortlessness is the key to the mind. So in meditation, actually we do nothing. We just keep our eyes closed, relax within ourselves so that we can experience the deep consciousness within us. So shall we do a short meditation? So before that, let's loosen up our body a little bit so that we can dive deep into ourselves. Can we all shake our hands? Let's shake our hands. You can shake your hands more faster. Wherever you are in the sitting position also, you can do this. More faster. Hand relax. Place your palms on the thighs facing the sky. Keep your eyes closed. With a gentle smile on the face, take a normal breath in and breathe out. One more deep breath in and breathe out completely. Become aware of the breath which is going inside and which is coming outside. And relax yourself. Wherever you are, you can sit comfortably with a gentle smile on the face. Keeping your eyes closed, observe the environment and noises around you. Observe the noise of the fan, noise of the vehicles, people talking around you. Whatever noises you hear, either at your workplace or at your home, observe all the noises. Accept all those noises and become one with them. Take a deep breath in and breathe out. Become aware of your body. Your body is a beautiful gift given by God and nature. Honor and respect the body. Keeping your eyes closed, observe your right foot, your right knee, right thigh and hip, observe the whole of your right leg, take a deep breath in and breathe out. Observe your left foot. Left knee. Left thigh and hip. Observe the whole of your left leg. Take a deep breath in and breathe out. Take your attention to your abdomen. Stomach and navel region. Your chest region. Right shoulder and right arm. Left shoulder and left arm. Throat. Face. Head. Observe your whole body. Take a deep breath in and breathe out. Become aware of your thoughts. Whether good thoughts or bad thoughts, let them come. Do not resist your thoughts. Be one with your thoughts. Take a deep breath in and breathe out. Become aware of your feelings. Your joy and your peace. Become aware of your feelings. Become aware of your thoughts. Become aware of the sensations happening in your body. Become aware of the environment and noises around you. Take a deep breath in and breathe out. One more deep breath in and breathe out completely. Whenever you feel, you may slowly open your eyes. Slowly, you may open your eyes. How is it? Good? How is the state of mind? Feeling good, fresh?
Yes, madam.
Nice. See, it's not that we don't have human values or human values have to be learned somewhere. See, love, compassion, caring, sharing, all these human values are there right from our birth. But due to the nature of our work, we don't pay attention on the human values. But human values play a very, very important role in building a violent-free society because society is something which affects an individual. So, if we can spare a little bit of time and if we can dive deep within us with some techniques such as meditation and all, it reinstills the human values and it helps us to create a violence free and stress free society. Because being faculty members, you all have so much of responsibility, not just providing information to the students, you're also responsible for creating a violence free society. That's why a little bit of attention on the human values when you are teaching to the students is very much essential. I hope many of you also pay a little bit of attention on the human values. But if you can meditate for some time, at least for 10 minutes or 15 minutes a day, it helps you to have a calm and peaceful state of mind so that whatever the human values which you are teaching, it practically helps the students to implement in their life. Hope this session, you might have enjoyed this session, this small session, and it's very useful to you. Thank you, everyone. Thank you, sir.
Thank you, ma'am. Thank you for the wonderful lecture on human values and wonderful guided meditation. So if there are any quick question can be asked.
Madam, excuse me, madam. Yeah.
Yes, sir.
Madam, actually, you said that meditation now. Yeah. Is there any number of time which is for it depends upon the age? So there will be some minimum time we need to spend like that. So can you give clarity on this? 30 minutes or
Yeah, normally it's always good to do meditation twice a day. One during the time of sunrise and during the time of sunset. Why twice a day means morning time, your mind will be fresh. So when you meditate, the impressions which are there in you that will be cleared, and throughout the day it helps you to carry on all your activities, whatever the activities are there, it helps to carry on all the activities. And during the sunset, actually sunset is the time, according to Ayurveda, where we need to close all the activities, because after 6 o'clock actually it's the time to take rest. So, whatever the impressions are there at the end of the day, it clears during meditation in the evening. So, it's always advisable to do meditation once in the morning and once in the evening. But if you don't have time, at least once a day, it's better to do meditation. The duration can be 20 minutes. It's not that you have to meditate for 1 hour or 2 hours, just 20 minutes of meditation, because 20 minutes of meditation will be equal to 6 hours of sleep. If you know to meditate on your own, you can do meditation on your own, or there will be a number of guided meditations on YouTube. Actually, in Art of Living also, we have so many guided meditations on YouTube. Just you can search meditations by Sri Ravi Shankar. You have so many guided meditations. Even 10 minutes meditation is also there. If you don't have time, at least that 10 minutes meditation also you can do.
yeah. Thank you, ma'am. Thank you.
So thank you, ma'am. So with this, we come to end of today's topics. So I thank all participants. So with this, let us close this today's session. and we will meet tomorrow. Thank you very much.
Thank you, sir. Yeah.
Thank you, everyone.